Thank you, Angelo, and thank you to the MIT Energy Initiative for the chance to be here and be a part of this panel. My goal today is really just, in some ways, just kind of just set up the others. So kind of maybe whet your appetite for wanting to dive deeper into thinking about a potential supply of biomass as an energy feedstock. I've had the pleasure over the last few years to dive into this question in detail and really try to think more about the role it can play in deep decarbonization. So trying to move away from thinking about what might a potential ton imply in terms of its implications and what that might cost, but really getting into the kind of scale that is being suggested in these deep decarbonization pathways on a global as well as a regional basis. So you've had the session one, so I think everything's been set up pretty well in terms of highlighting the potentially prominent role that bioenergy could play, and probably also raise some skepticism about that role. What we've seen, of course, is not only that prominent role, but we've seen characterizations of its potential value as a decarbonization strategy, where we've seen, like, for example, in different kinds of cost metrics like carbon prices or in consumption losses, that having bioenergy, and not just bioenergy with CCS, but bioenergy generally, could be a significant factor in terms of the cost effectiveness of pursuing aggressive climate goals, as well as the viability of those goals and whether or not they're even sort of attainable. So we can see that essential role. The chart on the right is just giving you more data points here, highlighting that in, for example, 2-degree scenarios. Those are the black dots here. This is some older work. The potential role that biomass could play in terms of total primary energy by the middle of the century, potentially reaching as high as sort of 30 to 40% of overall energy use, and by 2100, that use even growing larger, and a large fraction of that bioenergy being BECCS, and that's what's in the lower set of charts there. So bioenergy as a whole and bioenergy with CCS potentially growing in its importance and prominence and value as a strategy over time. Of course, we also see that these dots are scattered, and this is just one example. You can look at a variety of studies and the work, whether it's a 1.5 degree report from the IPCC or what's developing now in the AR6 context. We see a large variation in the results in terms of how bioenergy overall and bioenergy with CCS are being deployed. So that raises questions about why is there such significant variation. And of course, there's these various concerns, environmental and social concerns associated with just simply supplying the biomass, the kind of volumes that are suggested by these energy deployment results. One of the things that's important to sort of recognize in looking at these kinds of results, like the dots on these charts here, or the things that you've been discussing in the first session, is that those are market equilibrium outcomes. So you're seeing how a model, after thinking about the available supply of biomass and the demand for bioenergy in the context of a broader energy solution, in the context of a broader decarbonization strategy, essentially could fit. So where does it fit in that cost competitive portfolio of potential options? In that context, we actually know very little about the underlying modeling of the biomass supply. So we're only seeing these equilibrium market outcomes, and we see that interaction there playing out between the supply and demand, but we don't actually have a very good understanding of how biomass is being produced or the dynamics associated with providing different kinds of feedstocks in different parts of the world. So with that in mind, and really trying to better unpack bioenergy as a whole as a potential strategy for long-run decarbonization, a few years ago, we initiated the third study of the Energy Modeling Forum, so EMF 33, and that had a broad focus of trying to assess the viability of large-scale deployment of bioenergy. And we went about that by, one, assembling sort of a team of international modeling groups to explore this question, and two, going about exploring this question in terms of two different kinds of experiments. One set of experiments focused specifically on isolating the biomass supply dynamics within the models, and another set of experiments focused on evaluating and unpacking the bioenergy demand side of the models. So that has to do with getting into how technologies are specified, what kinds of opportunities there are for trade, what's happening in terms of deployment within particular sectors, and the role it can play in decarbonizing transportation, for instance. On the supply side, thinking about sort of, well, how are models even thinking about where are the cost-effective supplies? What might be the types of feedstocks in what parts of the world? What might be the implications of providing that biomass? How might those implications potentially be managed? What does that imply for the supply itself? And then ultimately, of course, how does it affect its availability to the energy system and how it might be utilized in the broader decarbonization strategy? So that was EMF 33's overall objective. And it's resulting in a number of papers that are coming out in a special issue of Climatic Change. And just give you a lay of the land here in terms of the type of papers. There's overview papers in this context with respect to the biomass supply assessment. So this is really an intermodal comparison, really focused on isolating that biomass supply production aspect within the models. A bioenergy demand assessment focused on an intermodal comparison of the bioenergy demand side, the technologies and so on, the markets. And then some cross-cutting papers focused on the individual issues. Again, model comparisons, but really trying to sort of dive more deeply into particular topics that are of interest to the overall discussion and to policy making. And then finally concluding with some individual papers where individual teams are able to use their own model to go a bit further in exploring some specific issues. So I'm giving you this lay of the land just to give you some context for what I'm going to be talking about in the bulk of my presentation. I'm going to focus specifically on what's highlighted in blue here, the biomass supply assessment, and hopefully that becomes nice fodder for the rest of the panel discussion for today. This is just a slide that's going to be available to all of you listing the different papers and their titles, and then there in blue again is the paper that we're going to be talking about today. So let me go right into this biomass supply assessment. This was a really interesting exercise because we were asking the modeling teams to do something they had never done before. And like I said, what we were trying to do is really isolate the biomass supply production dynamics within their model to get down to how they think about the availability of different feedstocks in different parts of the world, and do it in a way that we can make direct comparisons from one model to the other and be able to have something to say about what kinds of uncertainties are there, why are there differences, get into some of the individual idiosyncrasies of the models to help explain some of those differences and so on. What we did is to be able to choose that, we actually had many rounds of scenarios in trying to actually hone the modeling scenarios in a way that it would allow us to isolate that supply. It turns out to be pretty hard to separate the supply story from the demand story. So cutting off the demand side of the models essentially was one of the key design features associated with the exercise. So really trying to remove the influence of technologies or potential constraints associated with markets or trade patterns or penetration assumptions, those kinds of things, and focus simply on the biomass supply. We also had to identify which supply we were interested in. We were interested particularly in second-generation cellulosic feedstocks. So that doesn't mean we stopped modeling other kinds of feedstocks like first-generation, like corn and oils and things like that. But we were really trying to look at what might happen if you try to increase the demand for these second-generation cellulosic feedstocks. And we had two different kinds of experiments in the end, quantity experiments that are systematically for each of the models, increasing the demand for bioenergy over time, so biomass over time, out to 100, 200, 300, or 400 exajoules by the end of the century. And we also have price experiments, and so where we can introduce a biomass price, a farm gate price, and see what kind of supply would be available at that price. I'm going to spend most of my time talking about the quantity experiments here because not all the modeling teams were able to run the price experiments, but the two of them together provide a lot of useful information in being able to better think about how models are seeing biomass. How do they think about it in terms of its cost, in terms of its availability, in terms of its implications. We also ran sensitivity experiments off of the primary experiments where we looked at the role of land-based greenhouse gas mitigation. So if we provide incentives for storing carbon below ground or above ground, incentives for reducing land-related non-CO2 emissions, how might that affect the biomass supply? Likewise, most models have some sort of land protection assumptions in their default mode, and we wanted to remove those. So future sort of assumptions about lands that might be set aside, we wanted to remove and allow the models to actually, from a cost point of view, determine what lands are accessed or converted when you're talking about increases demand for biomass. So the takeaway here is that this is more of a diagnostic exercise, really trying to elucidate what's happening in the models and how they think about biomass supply, and trying to provide some greater transparency to the models to be able to have more insights and be able to interpret the integrated results, the kinds of things that you were talking about in the first session. So we started by looking at how the models think about the cost-effective distribution of biomass in the future. So this is simply looking at the same scenario. So all 10 of the models here are running a scenario, in this case, of biomass demand increasing to 100 exajoules per year in 2100. And these charts are showing you the distribution of that biomass supply as determined by each of the models on simply cost basis. So where do they see the least cost biomass in different regions of the world, which are represented by different colors, and in terms of different feedstock types, which are represented by shading in those colors. So you'll see three potential shades in any color, like in blue, where the lightest color represents residue-related feedstocks, the middle color represents energy crops of some kind, and the darkest color represents managed forest feedstocks. So the big takeaway here, when you look at this chart, is that the models see the world very differently in terms of where might be the least cost biomass, in terms of what regions of the world that biomass might come from, and in terms of what kinds of feedstocks might be the least cost feedstocks for meeting this prescribed level of demand in the future. And we could get into the details here in terms of which models are doing what. I'll just highlight a couple regions just to help you sort of see some of these differences. Red represents Latin America. So you can see some models are drawing heavily on Latin America, such as the image of Magpie at the bottom in the middle. But some models barely even touch Latin America or don't touch it at all, such as FARM and AIM and BET. Some models are relying heavily on energy crops. As a matter of fact, a large number of them are. Some models are relying more on residue streams, such as grape and BET. So there's a lot of different kinds of individual stories that are already coming out. We simply look at just where is the least cost biomass across the world in terms of the different feedstocks. We looked at the same picture, so taking that information on this slide and turning it into the first column on this figure here, and then looking at how might that picture, that distribution, that pattern of biomass supply change when we increase the level of demand. So moving from 100 exajoules in 2100 to the next column, which is 200 exajoules in 2100, or 300 exajoules, or 400 exajoules in 2100. So we're talking about increasing levels of demand out over time. This is a linearly increasing amount of biomass out to that particular exajoule level in 2100. And we can begin to look at any one of these models and see that the patterns will shift. So the models are seeing as the demand grows in these different scenarios that they need to be looking to other regions and potentially other feedstocks to meet that level of demand out into the future. The same takeaway here in terms of the models behaving very differently in terms of where they see the lowest cost feedstocks, and also responding very differently as we move to these higher level of demands. So we see some different levels of response, both some nonlinearities in how they're behaving, some shifts from one region to another, some shifts from one feedstock to another. When we try to unpack this and get a better sense of where it's coming from, we have to go all the way back to how the models are specified. And we see immediately differences in the feedstocks that they're modeling, in the structure of their models, in the way they think about land conversion opportunities, in the way they specify the productivity of land and the density of carbon associated with those lands. Those things matter, as well as the dynamics. So how do they think about the markets for lands, for example, markets for not only the energy-related commodities, but the other land-based commodities. And all those factors are contributing to the kinds of pictures that we're seeing here. So, of course, we're not only interested in the cost effectiveness of feedstocks and where the cheapest feedstocks are, we're interested in the potential implications of providing biomass. So what we have here are the implications in terms of land-based CO2 emissions in the chart on the top, land-based N2O emissions, the chart in the middle, and global aggregate non-energy crop price effects. And that's the chart down at the bottom on the right. One of the takeaways here is that as we're increasing the level of demand, so if we look at the top chart in CO2 here, and each of the models here has essentially results for increasing levels of the demand for bioenergy. So from the 100 exajoule in 2100 to the 400 exajoule in 2100. And we see pretty much from all the models that as we increase demand, we see an increase in land-related CO2 emissions. And these are cumulative emissions through the century. Similarly, we see an increase in N2O-related emissions. Not all the models are reporting on N2O emissions, so we don't have results from some models. But for those that do, we see the same pattern in terms of increasing the demand for biomass is leading to increasing emissions of both CO2 and N2O emissions from the land. And we see a similar kind of story when we talk about the non-energy crop price effects. So increasing the demand is leading to higher commodity price effects on the non-energy crops and in agriculture in general. So that's interesting. Of course, we see very different magnitudes in terms of the effect. That's going to impact how those models perceive biomass. Are you getting a big emission signal or a small emission signal? The pattern in terms of regions corresponds pretty well, of course, with what we saw on the previous slides with respect to where that biomass is coming from. But we also see some variation, which of course depends upon how you characterize the carbon content of those lands and the productivity of those lands for providing those biomass feedstocks. So of course, behind those emissions and price effects are land cover change stories. This is showing you what's happening in terms of land cover shifts in this 300 exajoule case. So just one of those particular demand scenarios. And looking across the models, we see in red, all the models are adding energy cropland. So as the biomass demand is increasing over time, they're all adding more energy cropland in red. And three of the models over on the far right, BET, GloBiome, and NLU, are also all adding managed forest lands, and that's in yellow. What's particularly interesting here is where that land's coming from. So if we look below the x-axis, we see what lands are being converted. In gray is other forest lands. So this is the non-managed forest lands. In blue, we see pasture lands, and in orange, we see other natural lands. And in green, we see non-energy cropland. So gray is very much prominent in pretty much all the models. So that's the other forest. We see pasture in some of the models is more prominent than others. And interesting, we see only a relatively modest effect compared to some of these other land cover types with respect to non-energy cropland. So the models are all interested in energy crops and energy cropland to support those energy crops. Some are also interested in managed forest related feedstocks. And where they're getting that land from varies from model to model, having to do with all these different factors in terms of how they characterize these opportunities for converting land. So that's a lot of information, and one of the challenges for us in this study was trying to come up with some compact way of thinking about the narratives or the storylines with respect to each of the models. So we were trying to come up with summary metrics so we could basically think about the narratives coming from each of the models. This is, of course, not meant to be what's happening in any particular year, but it's a way to kind of at least begin to make some comparison across all these different metrics that are of interest. So what this table is representing is the per exajoule effect of modern biomass that's supplied and the average effects. So we have average effects in terms of for that exajoule of biomass supplied, what fraction of it is energy crop residue or forest-related feedstocks, what kind of changes are there on average with respect to cropland and forest land and other natural land, and then also what sort of average changes with respect to land-based CO2 and land N2O emissions, and ultimately these commodity effects in terms of non-energy crop prices. I've highlighted one here, and I'll compare it to a couple others in a second. The farm model. So the farm model was only modeling energy crops as a feedstock. So for every exajoule supplied, of course, it's entirely energy crops. And as we go across that particular row, we see it's then utilizing on average about 800,000 hectares of lands, croplands. It's actually reducing forest land. It's adding about 800,000 hectares of cropland. It's reducing about 100,000 hectares of forest land on average. It's having no effect on other natural lands. it has a positive land-based CO2 implication, and a relatively modest effect on commodity prices. And we think about comparing that, and that's where these metrics become particularly handy, is we can think about other models that maybe have similar characteristics. So MITEI, for example, also was modeling only energy crops, but getting a much larger effect in terms of additional croplands to support those energy crops, the loss of forest land, the loss of other natural lands, and pretty big CO2 and N2O stories relative to farms, certainly, and many of the other models, as well as pretty big price effects. So these behavioral differences across the models stand out in this context of using these kinds of metrics. And just one more point of comparison, GloBiome, which has a diversity of feedstocks that are coming into play. So each exajoule supply is about half energy crops on average, but also has significant residue and forestry-related feedstock components to it. You're getting a smaller cropland expansion area, no net change in forest. As we saw on the previous slide, it's actually swapping one forest for another. And it's actually seeing an actual reduction also of other natural lands, a smaller CO2 signal from the land, and even a reduction of N2O emissions. And that's a pretty interesting result having to do with how we think about what's happening on agricultural activities, in particular as these land cover changes are occurring, and a modest price effect. So it's a nice way to begin to think about, like I said, the narratives in the models and the differences in those narratives across the models. And it helps us then think about how some of those structural and modeling dynamic differences are playing out in average terms. So one of the other things we were interested in is how might managing these externalities affect the biomass supply. So if we think about trying to essentially address those CO2 emissions that might occur on the landscape, so potentially putting incentives in place to store carbon in soils, store carbon above ground, reduce N2O emissions, reduce non-CO2 emissions, including N2O. What might happen to the biomass supply? This is showing you how feedstocks might shift in the case of the 300 exajoule per year scenario, where we now have a carbon price incentive for land-based mitigation. It's a $20 per ton carbon price, rising at 3% per year. What we see across the models is the models are adjusting in very different ways. Not surprisingly, some models are actually adjusting quite a lot, like the image model down at the bottom. You're getting much larger shift in how the composition of that feedstock. So this is just showing how the feedstock supply is changing. So it's moving where feedstocks are coming from, away from Latin America to other regions. Other models have much more modest shifts. And some models are moving away from energy crops towards residue streams now that there's an incentive for the land-based mitigation. And some models are actually also swapping where forest-based feedstocks might come from. So not necessarily moving away from forest-based feedstocks, but swapping where they might come from, like BET in the upper right-hand corner. So pretty interesting in terms of how the models behave when we think about pricing the carbon and pricing the other emissions on the landscape. We looked again at these other metrics associated with what's happening to CO2 emissions and N2O emissions and the non-energy crop price effects. And that's what's there in those three different charts. But this time for each of the models, it's showing you the 300 demand scenario, so the 300 exajoule per year demand scenario, without simply a biomass demand scenario, or with a land-based mitigation scenario, that's the C, or with land protection assumptions, so these in the model's default land protection assumptions, or with a combination of land protection and carbon pricing assumptions. You kind of look across to where some of the models were able to actually run all these scenarios and report results for all of them. We see that these other assumptions in terms of controlling these externalities, whether it's putting a price on land-based carbon or it's trying to set aside lands and protect them, can have a pretty noticeable effect on land-based emissions as well as on the crop price effects. So they could be fairly effective in not only reducing land-based emissions that could be occurring with biomass increases in biomass supply demand, but they could result in overall net uptake on the landscape, depending upon the model and how they're thinking about those incentives. The other thing we see is that these incentives, when combined with the biomass demand, actually lead to pretty dramatic increases in food prices. So down at the bottom, when we go across from these different scenarios, we see relatively small changes in food prices in just the biomass supply scenario. And when we add these other constraints or incentives with respect to land-based mitigation or land protection, those price effects become significantly larger, in some cases a couple orders of magnitude larger.
Steve, sorry to interrupt you. We are getting close to the time, so but you can finish what you have to present, but just remember that we are getting close to the time.
Good. Thanks, Angelo. So I just wanted to, I have one slide and then the concluding slide, but we've used those insights in terms of better understanding of the supply to think about the integrated results. So these are actually showing you these market outcomes. This is the biomass that's being demanded in a 2-degree scenario. So the standardized 2-degree scenario across all the models, and presenting what it is they're actually using in terms of biomass supply from the different regions in terms of the different types of feedstocks. And with the insights we have about the supply side and how the models are thinking about the potential availability of those feedstocks, we now have more insights into sort of these kinds of results. So for example, the farm model, which has some of the largest biomass demand in this chart, has very inexpensive biomass in its supply modeling. And that's one of the reasons versus the AIM model, which has very expensive biomass. So simply just on a cost basis alone, that's part of the explanation in terms of those dramatic differences between AIM and farm. We also see how the models are responding to the land-based mitigation incentives, which are on in this integrated context, as well as the land protection assumptions are having a big impact in, for example, how Image and Remind think about where feedstocks are coming from and also the types of feedstocks. So with that, I'll just wrap up and say that this exercise has actually been quite enlightening in terms of better understanding of the biomass supply and helping us think about individual model outcomes and differences in uncertainty. They also found that there's little consensus on where biomass could be cost effectively produced. That could be an indication of uncertainty, but also highlights the need to dive deeper into thinking about the specific opportunities in different parts of the world. And we did one robust finding was we found directionally consistent implications in terms of providing more biomass in the future. We saw that biomass supply was dominated by residues and energy crops, but managed forests is really not considered that much by most of these models. 3 of the models were considering it in a legitimate way, and that's something I know that the other panelists will be talking about, and we want to think a little bit further. Just in managing these land-based externalities, we saw that it has an implication in terms of the biomass supply mix and its location and where it will come from, and as well as societal costs. So trying to address those externalities or try to address them on their own will have their own implications in terms of cost for society, including food prices. And then I just mentioned that the biomass supply and integrated results sort of highlighted the fact that there are trade-offs that we're really going to have to address. So if we think about using biomass to address climate change, we're really going to need to be thinking about these trade-offs and thinking about how to manage them. And what we find from the models, so the models are not only producing biomass, of course, but they're thinking about these externalities and pricing them and finding it's worth it. And that's, to me, highlights the importance of these kinds of models. So while they get results that may be difficult to understand and needing a lot of work in terms of providing better transparency, they do provide us with a perspective that we can't get anywhere else. These are the only frameworks that really consider the full geographic and temporal scope necessary to think about managing the climate system, right? We know the climate responds to changes everywhere in the globe. We know that the climate system is responsive to cumulative effects over time. And so we really need to be evaluating biomass and bioenergy in the context of that full geographic and temporal scope. And these models are necessary to do that. And then I've just identified a variety of research opportunities at the bottom. One thing I'll just highlight is that the work that we've done in the supply context doesn't get into policy design issues at all. So we're assuming very stylized incentives in terms of land-based mitigation, just simply there's a carbon price everywhere in the globe, applied uniformly. Similarly, in terms of the biomass supply, we have simply this global demand in place without any sort of regional differentiation. So policy design is a huge issue in terms of how we evaluate these opportunities and think about the overall environmental and social implications. So, thank you, Angelo.